field. And we came to know that the relation between electric field and the force, electrostatic force, is if we take this Q not as positive test charge, then force, electrostatic force on that test charge per unit test charge is electric field, and the direction is same. The direction of the electric field is same as the force. So based on this concept, we'll try to understand more on this. If we have multiple charges, now suppose what exactly this means. Suppose let's take first example, we have plus Q charge and we have another test charge here. So if you want to denote this in terms of the quantities, these quantities, so we know that this is the unit vector. If I denote this R is a unit vector, and the separation between these two charges is R. All right, and both are positive. So I'll just write it here. This Q naught we are taking as positive test charge. So this is positive test charge, and we know it's a central force. So we know that this is acting along this line, and this is how it can be depicted. Similarly, if you want to figure out with this figure, this relation for electric field, at this point P, per unit test charge, what is the force here? Per unit test charge, what is the force? This is what E is, right? So if this is P, which is point of interest, and we have plus Q charge here, suppose, and we want to find here what is the electric field. The electric field vector we can show in this way, that is going to be away in the direction of force, and this is electric field E. So acting along this line of force, so we get an expression for this, and in the diagram it is shown in this way. So everything remains same, the unit vector, this R unit vector. Okay, so if you want to take a negative charge, suppose if you want to take a negative charge, how would you show that? So we would show that the same unit vector, and here you are placing a positive test charge, right? So test charge is positive, the source charge, so if we are calling this a test charge, let us call this a source charge, And why we are calling that a test charge? Because this is of negligible value, and this is a prominent source charge, because of which we get this electric field, substantial electric field, that we consider that in this situation. So if you want to show this, the unit vector remains same, R unit vector, and the force is going to be in the opposite direction, right? So the force is going to be attractive force. Now the force is going to be F naught in this direction. So if you remove the test charge, per unit test charge, and if you want to figure out what is the direction of the electric field, everything remains same. If this is the P and the separation is R, right, and the unit vector remains same, so the unit vector remains same, and the direction of the electric field would be in the direction of electric force, and this is E then. So this direction is going to be E. So these are few, just to understand this equation, the mathematical expression, just to understand with the diagrams, we can understand where the unit vector is pointing, where the direction of the force is, where the direction of electric field is. So you can take these examples there to understand clearly what exactly this means. So we have just taken one charge, right? And we have shown that this is a source charge, this is a test charge. Now suppose we take any test charge and we want to find what is the net electric field, right? So how do we figure out where the field is available? We place a test charge. When we place a test charge in the electric field, and if it experiences a force, then we call that the electric field exists. That is what it means. Now if you have Q here, Q naught, test charge, and you have multiple charges somewhere in the space all around. So by superposition principle, the same way that we applied the superposition principle in case of electrostatic force, we can also apply the same in case of electric field. So if you want to figure out what is the net electric force because of all, so we know that it's going to be F naught 1 plus F naught 2 plus F naught 3, and it goes on to n charges, right? The net force on the test charge. So if you divide this by Q naught, so if you divide this by Q naught everywhere on the left hand side and the right hand side of the equation, this is what we get by the definition electric field, net electric field on the test charge, right? So we can write this, the net electric field, the direction remains same, so we can point this vector in the equation, and we get this electric field is equal to E1 plus E2 plus E3. So vectorially we are adding all these separate electric field because of those charges on the test charge and until the last one. So this is where we apply the superposition principle to find what is the net electric field at the point P, which is point of interest, wherein we have put in the test charge to test what is the electric field. So electric field because of charge 1, electric field because of charge 2, electric field because of charge 3, all are added vectorially to get the net electric field. All right, so having understood this, now let's move on to find when we have a dipole, what does dipole mean? What are the quantities there, and how do we figure out what is the net electric field in two positions? So we'll derive an expression. If you keep the test charge in the direction of the alignment of both the charges, which is the axial position, and if you keep the test charge on the equatorial position, what is going to be the net charge, net electric field because of this configuration? So today that's the main topic that we are going to study about the electric field because of configuration when you have a dipole aligned on x-axis. So two positions we are going to take. One position would be the axial position, the other position would be the equatorial position. So suppose we keep the origin here and we keep these two charges on x-axis, right? This is the y-axis, this is the origin O, and we keep these two charges. One charge we keep here, suppose this charge is positive charge, and one charge we keep here, a negative charge. All right, and from the origin we keep this at the position, the coordinate of this position is A0 suppose, and the coordinate of this position is minus A0. So the dipole means that we too have these two charges of opposite nature, right, but equal in magnitude, and here the distance is A and this distance is also A. So we have the separation between these two charges which remains constant as 2A. All right. So before we move on, let us understand one very important quantity which is known as dipole moment. Dipole moment. Now it's a vector quantity, and this is defined as the product of the magnitude of the charge, which is Q, and the separation, which is A. And it's a vector quantity. So if we denote this by P, Q times 2A, right? And if you multiply with unit vector, so this direction of P dipole moment is from negative to positive. So we have this I cap denoting that this is in this direction, and we have this quantity defined as this in this manner, that this is a product of these two. So basically this is giving you a sense. This is giving you an electric effect which is produced by product of these two quantities. One quantity is the separation. This 2A is showing you the separation. Now remember, this separation is not variable, it is constant, right? The separation remains constant, and this is the charge, magnitude of charge. So what effect if you have a lower value of Q but you have high separation, right? So, and there's going to produce an electric effect. If you have higher magnitude but low distance, low separation, lower value of the separation, then it can produce the same value. So it's giving you that idea what is the effect, electric effect. And in many of those neutral atoms, in many of those bulk matter wherein all the atoms are neutral, the orientation at times are such that they develop this kind of dipole moment in such compounds. Say for example water molecule, right? So the oxygen that we have, we know that there are two hydrogen atoms combined with one oxygen atom. So there is positive, delta positive developed in those two hydrogen atoms which have just one electron on the orbit, and then we have this high negative with negativity oxygen atom developing slight negative charge. So we have this kind of separation which is fixed, and we have slight delta charges there. So it's sort of like dipole moment is defined to produce that, to give that sense of that effect, that is the electric effect, which is very important in quantitative analysis. So having understood this dipole moment, we'll now try to look into this same diagram that we have made it here, and we are interested to find, in this is the axial position, this is the axis, right? This is the axis. So anywhere, suppose here we place our point of interest P, and we are interested to find what is the distance here. So let us denote the distance here. So this P point of interest, wherein we want to find what is the net electric field, and this P from the origin is at a distance r, right? From here it's at a distance r. So if it is 2a, the separation, this positive charge from here to this point of interest P, what is the distance? So if this is r, and this we know this is a, this one is a, here it is a, so this distance would be r minus a. Similarly, if you want to find from P, what is the distance that we have this minus q charge placed? So this is a, and from here we have r, so this distance will be r plus a from here to here. So take note of this diagram, and then now we'll proceed to figure out at this point what is the electric field. So if we consider, suppose electric field E1 is because of electric field E1 is due to positive Q, and E2 is due to negative charge minus Q. All right. So we know what is the expression because of point charge, what is the expression for electric field E. If you have placed the test charge, it is 1 over 4 pi epsilon naught Q divided by r square, right? Q divided by r square. So this is the expression, and if you want to give a vector sign, we can have this relation. Now with this information that E1 is in this direction, right? E1 would be in this direction. Why? You have placed a positive test charge in this direction. So positive Q is going to repel this, and we'll have in this direction. Similarly, If you want to show what is the direction of E2, E2 would be in this direction. Why? Because it's going to be attractive force. So this is E1 and this will be E2. So what's going to be the net electric field here at P? That is what we are interested in. So vectorially we are going to add it. So we'll first find what is the expression for this. So E1 is going to be what? E1 is going to be 1 over 4 pi epsilon naught. It will be Q is that value, and what is the distance? It's r minus a, so it will be r minus a whole square. And if you want to vectorially indicate this is going to be in this direction in the positive x-axis, so we are placing I cap. This is equation 1 that we get. All right, now we can find similarly what is equation 2, that is for E2. Now the separation here is r plus a, so we'll get 1 over 4 pi epsilon naught, and here will be again Q, and here will be equal to r plus a whole square, and this will be negative I cap. This is equation 2. So by superposition, E net or electric field at P, since we have denoted it as P there, this is going to be the vector addition of these two electric field. So this comes out to be 1 over 4 pi epsilon naught Q over r minus a whole square, and this is plus and this is minus, right? So we can write this, no problem. This I cap first, plus 1 over 4 pi epsilon naught Q r plus a whole square, and this will be negative I cap, negative I cap. So this negative comes here, so we'll actually minus it, subtract it. So I'm just removing it, the sign here, and placing it here. So this is going to be the E net at P. So let's see what it is. If you take these two things common, 1 over 4 pi epsilon naught, and we take Q also common. So what's remaining is, here it comes out to be r plus a whole square minus r minus a whole square. And in the denominator we get r minus this one and this one. So it comes out to be r minus a whole square times r plus a whole square. All right, so this is EP. Now if you open the bracket, let me rub this and continue here. So now it becomes electric field at P is going to be equal to Q over 4 pi epsilon naught. So if you expand it, it becomes r square plus a square minus r square, right? It is plus, so it is 2ar minus r square minus a square, and minus will become plus here, so it will be plus 2ar, right? 2ar. And in the denominator we can use the identity directly, so it is r square minus a square whole square. This is what we get. So we see that this gets cancelled out, and we are getting what? We are getting, upon adding up, we are getting Q by 4 pi epsilon naught, and here we get 2ar, which is 4ar. I cap we should not forget, 4ar divided by r square minus a square whole square, I cap. Now 4a, can we write this in this way? So it could be written as 2a times 2. We can write in this way. All right, why we have written this way? Because if you look carefully, 2a and this Q with I cap. So here what do we get with P? So P is 2qa I cap, right? So if you want to remove this 2a, q and I cap, we are left with E P is equal to 2. Now R remains as it is, 1 R remains, and here it becomes P, right? In vector form we can write this, and this divided by 4 pi epsilon naught. Here we come R square minus A square whole square. So we can approximate this. Now this separation is too small as compared to R. So if A is very much small as compared to R, we can ignore this in denominator and we'll get there. So therefore, if we take this, let me just clear it down. So if you approximate this, we can write what is expression for electric field. When we approximate that A is very much less than R, it could be 2RP, and here it becomes 4 pi epsilon naught R raised to the power 4, right? If you put A is equal to 0, it becomes R squared, so R raised to the power 4, 1 R gets cancelled. So we get here 2P, here we get 4 pi epsilon naught R cube. This is the final expression we get for the net electric field that we have because of dipole at point P, which is at a distance R from the midpoint of the distance between these two charges. So we can write this magnitude. So this actually shows, now I'm writing it here. What does it show? It shows that this electric field, the net electric field at P, the magnitude of this is proportional to 1 over R cube. Why? Because this dipole moment P is constant, everything else is constant. So we get a very important relation that this electric field is proportional to 1 over R cube, or it's inversely proportional to R cube. So this is extremely important, and the way that we derived it is quite a reasonable way of figuring it out, what is the electric field at P. So take it down, it's important from examination point of view to understand how it works. This is the situation. You can write the situation is axial position, right? The situation is axial position. So the derivation shows that if you place the two charges, negative and positive, a dipole on x-axis at the axial position P, what is the net electric field at this P because of this dipole moment in axial position? Take note of this. Well, now let's try to figure out, if you have an equatorial position and the point of interest P is lying on the perpendicular bisector of the separation between the two charges, that is two equal in magnitude but opposite in nature, so what is going to be the net electric field at that point? So we'll use the unit vector notation again to figure out the net electric field. So let's take now an equatorial position. So we call this time kind of position as equatorial, and here we have y-axis here, suppose. Here we take minus q again, and we have origin, and then we have here plus q. And we take the y-axis here. Somewhere here, any point on this perpendicular bisector of this separation, again this is origin, so we have A here and we have A here. So that is how we have placed it, and the distance is 2A, that is the separation between the charges is 2a, and this is the point of interest P, wherein we want to find what is the net electric field at this point. So how can we arrange this? So now again this P is at a distance r from the origin. All right. From plus Q, if you want to see the vector, electric field vector, we know it's going to act in this direction. So somewhere, if E1 is the electric field because of plus Q, as we have assumed previously, so we can denote this in this way, that this will be the direction of electric field. Now, then we have now here minus Q, and minus Q, force is going to act in this direction, right? So we can denote this, if this is E1 vector, we can denote this in this direction. Y is going to be attractive force, so we are denoting this with yellow color E2. E2 is the electric field vector because of minus Q at point P. All right, so let us just use our reference again, the negative and the positive conventions. So here we are going to take this, the x-axis, right, in the positive direction. The other direction we take negative, and this is the y-axis we are taking. And suppose these two angles here, these two angles, this angle is going to be same as this angle by geometry, right? So if you consider this to be theta, it's going to be angle theta. So if these two references are same, parallel to each other, so corresponding angle would be same. So this is going to be again theta. And if this is theta, the alternate angle, this would also be theta. So now we see that E1 and E2 could be resolved into different components, the vertical and the horizontal components, and then we'll add it vectorally. So if you want to figure out what is E1, again, we'll just denote this direction. We are interested in this direction in the equation, right? So if this is A and this is R, this is going to be R square plus A square by Pythagoras theorem, right? Similarly, this distance will be equal to R square plus A square. The distance from minus Q to P and the distance from plus Q to P is same, and which is equal to under root R square plus A square. From where we got, just we have applied the Pythagoras theorem to get it. Now with this arrangement, we are interested again here, to be reminded, we are interested to find the net P, and we need to see what is this component, this component. So let's first write what is E1. Now E1, that is electric field vector E. This is going to be the sum of this and this. So let's figure out what is this first and this first. So this is going to be whatever E1 cos theta. This is going to be E1 sin theta. This one is going to be in the horizontal cos theta, and this component is going to be sin theta. So E1 vector is the summation of these two components, right? So we'll write this E1 as, E1 vector would be equal to 1 over 4 pi epsilon naught. Q is the charge, so Q. And what is the distance? Distance is same, root under root R square plus A square. R square plus A square. Okay. Now if we take this component, it will be J cap, here it will be minus A cap. So let's take E1 separated by E1, net E1 is going to be this. If you want to denote this component, it would be J cap, right? So J cap would be this sin theta, J cap, all right? And this plus 1 over 4 pi epsilon naught, it will be Q divided by under root R square plus A square. Now here it would be cos theta, and this will be minus I cap, right? Minus I cap. So one component is going to be in this direction, one component is going to be in this direction and the another component is going to be in this direction. So this is going to be the summation of these two vectorially. So the net E1 that we are getting is equal to, so let's use the same color. Net E1 will get, if you take these two common, it will be 1 over 4 pi epsilon naught q by r square plus a square under root, right? And this will be equal to sine theta, or say I cap if we take cos theta, minus I cap plus sine theta j cap. We are taking just common, right? Well, now let's talk about E2. Now if you resolve this into respective components, this is going to be negative j cap and again negative I cap. So we can have this equation directly written as 1 over 4 pi epsilon naught, here it will be q by r square plus a square one over 4 pi epsilon naught, it will be q under root r square ho gaya a square, and then we'll have here this component if we take I cap. So it will be negative I cap, it will be again cos theta negative I cap plus 1 over 4 pi epsilon naught q by r under root r square plus a square, and it will be sine theta negative j cap. So if you again take this common, so we can write in this fashion that 1 over 4 pi epsilon naught, here q we have taken common, under root r square plus a square, again we can take common, and then we can have here cos theta minus I cap plus sine theta minus j cap. So first equation we get for E1 is this in vector notation, and second equation we get these two. So the net would be addition of equation 1 and 2. Take note of this until they're here. Take note of the steps that we have followed using the correct vector notations, and then we are able to find these two equations, E1 and E2. So therefore E at P, which is here, the net is going to be the vector addition of E1 plus E2. So we'll add these two and we'll try to figure out what quantities gets cancelled out and finally what we get. So take down this and then we'll move ahead. I'm just rubbing this. So let us use the white chalk to denote this electric field EP is equal to this plus this. So first equation is this, so let's write it 1 over 4 pi epsilon naught q by under root r square plus a square, and then we have got here cos theta minus I cap plus sine theta j cap plus 1 over 4 pi epsilon naught. We got this equation, second equation, as q over under root r square plus a square, and then we have under the bracket cos theta minus I cap plus sine theta minus j cap. So let's again take common. So we don't have space here. Let me rub this diagram to make a space here. So we are getting the final expression as net electric field at P is equal to 1 over 4 pi epsilon naught, take everything common, Q divided by R square under root R square plus A square. And when we take this common, we are left with cos theta, or let's take negative here, negative cos theta I cap plus sine theta j cap minus, again it will be negative of cos theta I cap, and here's minus sine theta j cap. So we see that this gets vectorially cancelled out, sine theta j cap plus minus sine theta j cap, and we are left with 2 cos theta, right? Cos theta I cap, cos theta I cap. So let us write the final expression. It comes out to be electric field E at P is going to be 1 over 4 pi epsilon naught Q by under root R square plus A square. In the bracket we are left with minus 2 cos theta I cap, right? That's the only thing we are left with, and this gets cancelled out. So let's take the I cap out. We are left with cos theta. Now from geometry, if you see, so this was angle theta, and from origin this was A, and here we have here 90 degrees. This is angle theta. So what's going to be the cos theta value? Cos theta would be A over this. So let's write it. So therefore this comes out to be, from the geometry we'll write cos theta will be equal to A divided by under root R square plus A square. So this comes out to be 1 over 4 pi epsilon naught. Here it is Q. Then again it is negative here, so we'll take the negative sign. Let's take the negative sign out. So here we are writing negative. So it is Q times 2 cos theta is A over under root R square plus A square. And here also we have from the common quantity that we have taken out under root R square plus A square. So this is what we have. And remember, this is here. When we are writing this, in all this expression, we just need to remember this is whole squared. So we have missed out that. Let's make it up. So in all the expression, under the denominator is squared, right? So denominator is squared. Denominator is squared here. Okay, this is squared. This is squared. So we get root here out, and this would finally come out to be. Now again look at it, 2AQ, right? And I cap is also there. And we know this 2AQ, I cap is P. So we are writing it directly. It's going to be negative of dipole moment P divided by 4 pi epsilon naught. Now this comes out to be the expression as R square plus A square whole raised to the power root 3 by 2. So this is squared. We have removed the square sign. So 1 by 2 plus 1, it comes out to be 3 by 2 in power, and we get this final expression. So let me write it again. What we get final expression for the equatorial position as for equatorial position we get electric field P is equal to minus P over 4 pi epsilon naught R square plus A square whole raised to the power 3 by 2. Now again, if we approximate, let's put A, since A is very much less than R, so therefore if we ignore A, we'll get approximate value as, for a short dipole, so we can write it here, for short dipole, the net electric field E at point P we get as 1 over 4 pi epsilon naught into minus P, which is the dipole moment, divided by R square raised to the power 3 by 2. This gets cancelled out, which again comes out to be 4 pi epsilon naught R cube. So here again we see that this value is proportional to R cube. So here also we can write that this magnitude of the electric field, finally we are getting as, the magnitude of the electric field we are getting as proportional to 1 over R cube. This is the final expression that we get for the net electric field at point P, which is the equatorial position, and the equatorial position is the position, any position which is on the perpendicular bisector of the separation. So we have done two derivations, extremely important from examination point of view and to understand. So step by step we came up with this expression, and final conclusion is that this electric field is proportional to 1 over R cube in both the situations. This is how it is that we apply the superposition principle and we find the net electric field. So in the next lecture, be ready for another very important numerical problem, and then we'll move forward with Gauss law in electrostatics. Thank you.